I want to go over with your warm-up with you. So let's go ahead and take a look at this. So this first problem here, when we read what we got going on, we have one population. Okay, so because we have one population, then with some claimed percentages. So we just have one, we have the various categories. One population with the claimed percentages, that makes this a chi-squared goodness of fit type problem. Okay, now I want to show you the number one mistake that gets made that I want you to watch out for. I want you to check what your expected counts are. For A, it should be 4875. And the common mistake that gets made is people go 15% of 89, and that's not correct. It is supposed to be 15% of the total. So make sure you do 15% of 325. That's how you get 48.75. Okay? And then, of course, the next one is 30% of 325, and that's how you get 97.5. Okay. So that's the very first big mistake that I end up getting from students. Make sure you get that. Expected counts. Also, make sure that you label this expected counts, because I'm going to be referencing that later on in my conditions. I'm going to say, look at the expected counts above. Well, if you don't have it labeled, then I don't know where I'm supposed to look, and I don't know what those things are. All right, so let's go ahead and go through this. Yes?
Do we have to have the expected counts written down? Is that required?
Somewhere, yes.
Okay.
All right, so we do a phantoms model without the P. We do not have to define that parameter. So our phantoms model starts with H, where we say the null hypothesis, the professor's grades are distributed as the historical distribution says. So it matches what the professor historically has done. And the alternative is that the grades do not match what the professor has historically done. And now conditions. Because this is one population, I'm doing the conditions on this one population of her students. So random, I'm going to assume that these 325 students are randomly selected from maybe all of this professor's students. I don't know. Independent, and I don't know how far of a stretch this is. I guess I'm saying 325 would have to be less than 10% of all such professor students. So I don't know if this is all that she's ever had ever, because that seems like a lot to have over 3,000 students this semester. But these are, again, assumptions. So upon these conditions being met, then you know that this chi-squared model applies. Large enough. You can see from the expected list above, that is why I had to label that that's what the expected counts were, okay? Because I'm referencing that all expected counts are greater than or equal to 5. If I had listed them all there, that would have been fine. But somewhere I need to list them. So do not forget to conclude that the chi-squared model applies. And those were our assumptions in the phantoms model. Okay. So as we said earlier, it is a chi-squared goodness of fit because it has one population. And so now I went into my calculator, and here's how I did this. So I went into my calculator, and I went and I put the observed into L1, and then I put the expected into L2. All right, so that's what your lists look like. And so then so then when you do that in your calculator, you then put it into, you get the chi-squared goodness of fit, and upon doing the chi-squared goodness of fit, you had to put your degrees of freedom. How did you get your degrees of freedom?
Categories -1.
Good. So for this one population, categories -1. All right. And then when we put it in to our calculator, we get that chi-squared, which is quite large. And so, of course, a very high chi-squared is a very low p-value. And so then that's what I have written down here. So with the low p-value, what are we going to do? Reject that HO.
Wait, I'm confused. On this sheet thing with you, for goodness of fit, for degrees of freedom, it says just categories, -1, but then for the other ones, it's rows -1 times columns -1?
Yes, for goodness of fit, it's just categories -1 for degrees of freedom. And for the other two, it is rows -1 times columns -1 because they're multidimensional. And so then we obtained a p-value and we made a decision. And so then our conclusion, our statement of conclusion is, since the p-value is low, I reject HO, and I then have evidence of HA. So I have evidence that the professor's grade distribution does not match the historical distribution. All right, so the grades are being done differently. So if the grades are being done differently, then a lot of times I'm wondering, okay, well then what is actually the biggest deal? And so that's what the next question was. Which grade impacted your decision the most? So in order to do that, I did the standardized residuals. And these standardized residuals are observed minus expected over the square root of expected. Here are the residuals that I got. And so when I got those residuals, I made a statement to answer their question. It said, in particular, the A's have the largest residual at 5.76. So that answers their question, which impacted your decision the most. Now, I gave more information. I said, it appears as though the professor's giving A's and B's more than expected. And what made me draw that conclusion? That they're more than expected. The residuals are positive, good, and then giving out C's, D's, and F's less than expected. Okay, next one, on to the next page. So on this page, we find that we have males and females, and we're wondering if they do one particular category, and that is eat breakfast. So or do not eat breakfast. So our populations are the male and female, and our one particular category is they eat breakfast or they do not eat breakfast. So I went ahead and I figured out my expected counts because I'm going to have to do that. So, your calculator can do this for you if you have all the data. Sometimes you won't have all the data. And if you don't have all the data and you have to do it by hand, how do you come up with that expected value right there?
Row total times column total times total or divided by total.
Yep, row total times column total over total, which in this case,
Which would be all males that eat breakfast.
yeah, so it would be all males, 132, times all eating breakfast over the table total of 331. And so that's how this particular cell expected value was obtained. All right, so I wrote out and labeled my expected table. So since I have two populations, then make sure when you do your conditions, you're going through both populations. So here my null is that males and females eat breakfast at the same rate. My alternative is that the males and females do not eat breakfast at the same rate. And now look at my assumptions, please. Because this is about two populations, the males and the females, my assumptions are about both. The 132 males and the 199 females are assumed to be randomly selected. And independent, the 132 is less than 10% of all such males. The 199 are less than 10% of all such females. And those two sample groups, those males and females, are independent of each other. Now, here, you can see from the expected matrix above, that's why I had it labeled and referenced, that all expected counts are greater than or equal to 5, and that is met. So don't forget to summarize with your chi-squared model applies. All right, the name of this one was the chi-squared test of homogeneity because it was two populations with just one category. All right, where did you do the work for this one in your calculator? In the matrix, and I'll show you that in a second. But the results you get were 534 for chi-squared. List your p-value. And how do you get degrees of freedom again by hand? Rows -1 times columns -1. So my p-value is low. I reject HO. There is evidence that the males and females do not eat breakfast at the same rate. Now, the question did not ask you for any more information. But it is common that, especially when you reject the null hypothesis, that question might be posed to you. So I went ahead and I wanted to demonstrate for you what you might do in that case. If they had asked you for more information, of course, you would do your standardized residuals, which for each cell is your observed minus expected over the square root of expected. And then I did that for each one. And I'm just going to make a generic or a statement about what I observe. And I can see from these standardized residuals that the men eat breakfast less than expected and the females eat breakfast more than expected at a higher than expected rate. So again, this particular problem did not ask for that specific information, but it is a common question when you reject the null to get more information. Okay. Real quick, I wanted to show you the calculator information for the matrix. So for the matrix, we were doing this. We were going into matrix A, and we were going over to edit it. Okay, and then after we did that, we went and we put it in a 2x2 matrix. Hey, when you put it in the matrix, don't put the totals. Okay, don't put the totals. And then after we did that, we went to our chi-squared menu and did a chi-squared, or our test menu, did a chi-squared test. And then that's finally how it gave us our results. Okay.
Chi-squared model applies.
And so that is what we get when our chi-squared model applies. Okay, any questions on that warm-up? And there you go.